given a seminar talk in BIMSA quantum symmetry seminar. And my talk today will be based on a series of joint work with Hao Zhang. And so two of them are already put on archive, and one of them, like the second one, as you can see, the second one is just posted on archive this morning. And we plan to have at least 3 papers in this series, so this project is still not yet finished. And okay, so I will start my talk by talking about modular invariance, because modular invariance is a central theme in the story of vertex orbital algebras. So an early breakthrough in this topic is a theorem due to Yongcheng Zhu. It says that, okay, assume that V is a so-called pseudo-q-traces and rational BOA, then the set of characters, Q characters, defined by taking the trace of the Q to the power L0 minus C of 24. C is a complex number called central charge. Then this function of Q extends it's a kind of they form a kind of modular invariant space. It's a kind of vector value modular form. But more generally, what Zhu really proved is not just about these kind of functions, but are about, I mean, you should take care of not only these functions of Q, but you also have to take care of these linear functionals of V. So here V is a vector space as a VOA. It is a vector space V. So it is, you should really care about the function from V times H. H is the upper half plane of the complex plane to the trace, and it's defined by the trace of the vertex operator with value V equals 1 times the Q tau to the power L0 minus V over 24, where Q tau is defined by e to the power 2 pi I times tau. So this is a kind of, it spans a kind of vector space, which is modular invariant. So the advantage of working with this space instead of the characters, the one here is that, so here it is, you can see that for different choice of irreducible modules, and they are linearly independent, but here they are not necessarily linearly independent. So this is, in some sense, better, has a better mathematical behavior than this one. So that's why it's better in BOA. It's better to, I mean, if you work with abstract story, then it's better to work with this one. But if you want to do explicit calculations, then you probably will start by looking at this kind of stuff. And here, pseudo-q-traces is a finite condition which ensures, for example, that my VOA has finitely many irreducible objects. And rational means that every module is completely reducible. It's a finite different sum of irreducible objects. Okay. However, if I drop the rationality assumption, I only keep the C2 condition and I remove the rationality, then this modular invariance property in the formulation of Zhu does not hold. Well, because it has been long observed that if you take, for example, you fix a module and you take just take the Q character and you apply the modular transform, you get a new function of Q or function of tau. Then this new function will contain some factor which is the log of Q tau. So originally this expression is only a fractional power of Q. If you take the modular transform, you will get some log Q. So which means that this space is no longer modular invariant. So which means that if you still want to prove a type of modular invariance theorem, you have to generalize the Q characters. So that's the reason, that's one of the main reasons that Miyamoto in 2004, he generalized the Q-traces to the so-called pseudo-q-trace. Well, he kind of replaced this ordinary trace function by a more general type of trace, more general type of symmetric linear functional called pseudo-trace. And he used this pseudo-trace to construct this expression, and he showed that if we use these pseudo-traces, then they form a vector space which is modular invariant. So this is one of the main results in Miyamoto's paper in 2004. And later, Miyamoto's formulation of pseudo-q-traces were simplified by Arika and Gainutdinov-Runkel. This is the background of my talk.
So this here, the M is not required to be projected. It's
M is arbitrary.
Arbitrary.
Well, I think I think if you want to define things, you want your M to be like projected over a subalgebra of the endomorphic algebra, but it's not necessarily projected over B.
Okay.
Yeah. So you see that the usual q-trace, I mean the q-trace of this one is it's basically just a contraction, right? So it's quite compatible with the zoning construction in Segal's definition of CFT. However, it seems that pseudo-q-traces or pseudo-q-traces are more complicated than the ordinary q-traces, and it seems that pseudo-q-traces were not discussed in Segal's formulation of CFT. So the question is, did Segal really miss something? So the goal of my talk is to give you the answer. No, Segal didn't miss anything, but slightly adjust Segal's formulation of zoning construction. We can recover the pseudo-q-traces. So the main goal of my talk is to explain this, how to incorporate all these pseudo-trace stuffs into the framework of Segal's zoning construction. Okay, I will explain, in particular, I'll explain how this algebraic definition of pseudo-traces matches the Segal's geometric framework, and our explanation will be based on the theory of conformal blocks. And let me first mention that the traditional approaches to the theory of conformal blocks cannot recover pseudo-q-traces. So in what follows, what I will do is that I will show you what our formulation of conformal blocks is, and I will point out our difference with the traditional one to show you what kind of ingredients should be added in order to recover these pseudo-q-traces. Okay. Okay, so let me turn to the conformal blocks. So these are the basic data of the conformal block. So first of all, in my talk, I will always assume for simplicity that my VOA is pseudo-cofinite, although some of the results could be applied to a broader class of VOAs, but I will, for simplicity, assume that I will focus on these pseudo-cofinite VOAs. And to talk about conformal blocks, I have to first fix a compact Riemann surface, not necessarily connected, and I have to put some mark points to see. So here, P is a compact Riemann surface, possibly have several components, and x1 to xn are some mark points. So if you look at this picture, then this picture has 3 mark points, and at each mark point, I choose a local coordinate eta. So local coordinate just means that it is a holomorphic injective function. For example, eta1 is a holomorphic injective function defined on a neighborhood of x1 such that its value at x1 is 0. So roughly speaking, it maps a neighborhood of x1 to an standard open disk, and it maps x1 to the origin. Okay, so this is the meaning of local coordinates. And based on this geometric data, which I call the endpoint and compact Riemann surface with local coordinates, I can talk about conformal blocks. Okay, so I also need to associate the modules. So here, for example, if I have 3 mark points, then I have to choose a module W to be a module of V to the tensor power 3. So in general, if I have n mark points, then W should be a module of V nth tensor power of B. And a conformal block is a linear functional on this vector space W, satisfying some covariant property or invariant property, which is defined using the geometry of compact Riemann surface and the vertex of the algebra and the modules. Okay, so the precise definition is quite complicated, so I will not go through these details, but I just want to show you these the basic data I need in order to describe what is a conformal block. And here I want to point out one very important difference between our setting and the traditional setting of conformal blocks. So traditionally, when people study conformal blocks, people like to take this W to be a tensor product of V modules. But if you take W to be in this form, then you cannot cover the pseudo-q-traces. Okay, so in order to get pseudo-q-traces, we have to consider these modules of tensor products VOAs, which cannot necessarily be written as the tensor products of V modules or their direct sum. So this is a very important difference between our setting and the conventional setting. Okay. Okay, so next I will talk about solving. So as you just look at the solving of Riemann surface, then it's very easy to understand. It's just the where if you solve these 3 points, then you remove a small disk, and you glue them together. The way you glue them is defined by their local coordinates. Okay, so the local coordinates, it describes which formula you need in order to identify the point here with the point here. And after you glue them, you will get this. In this example, you will get a genus 2 surface from a genus 1 surface. So you see that for this picture, it has 4 mark points. But in order to define the corresponding solving of conformal blocks, you cannot choose a module of V tensor 4. Instead, you have to choose a module of V tensor 2, a V module X, and a V module X prime. And your conformal block should be a linear functional on W tensor X, tensor X prime. So X prime is the VOA people will call X prime to be the contragradient of X, but basically it's the gradient dual, a kind of dual representation of X. So it is a linear functional here. Okay. So in this picture, so W is a V tensor 2 module, X is a V module, X prime is a V module. But if you look at this picture, then W is a V tensor 2 module. Both X and X prime are also V tensor 2 modules. So here I glue these 2 points together. And I get a genus 3 sphere from a genus 1 sphere. This is what I call the self-solving, because all these mark points belong to the same component. But it's more important in our story. It's more important to consider the disjoint solving, which means that these 2 mark points that you need to solve the Riemann surface belong to different components. So the other settings are similar. You glue them together, you get originally you have 2 components. Each component are genus 1. You glue them together, you will get a forget that one. You just look at the bottom. Here you get a genus 3 stuff. Okay, so forget this one. The solving of X should be this genus 3 stuff. Okay, so again,
the solving of the top one is this.
Oh yeah. The solving of this one is this. And the solving of this one is that one. Yeah. Okay. Okay. So any questions so far?
Can I exchange the self-solving? So let's say X is tensor of 2 V modules. Then I can still exchange them first and then solve them, like in the second picture.
You mean this solve with that one and this with that one?
Exactly.
Good question.
But then you can do it in 2 steps. You first change X by a homomorphism, then so like.
Yeah, but you need the exchange to be the morphism of the copy.
Let me think about this. Can I do this?
Maybe there's some value for tells you that you can.
Let me see. Okay, so when I say that, let's say X is associated to these 2 points. So X is a, let's say X is a B tensor V module. So these 2 actions are described by 2 vertex operators. Let's say this is Y1 and this is Y2. And I have another X prime. It is also B tensor V module. Well, if you want to, let's say, so this one with that one, you have to switch the actions. I mean, when you define the conformal blocks, the conformal blocks are defined by linear functionals satisfying certain invariant condition. And to define that invariant condition, it really matters let's say which one is for y1 is which one is for y2. If you want to solve this one with Segal, you have to put the y1 action here and the y1 action here, and then you can do them together. No problem. Okay. So next one, this is a theorem that in the paper that we have just put on archive this morning. It's a conversion theorem. It says that based on the setting in the previous page, suppose that the psi is a conformal block associated to W tensor X prime. This is the Riemann surface before solving. This is X is the one before solving. And we can define a single solving, which is a where you just take the contraction. It's very simple. The formula is very simple. And it's convergent. And it's not only convergent, but after you take the contraction, you get a new linear. Once you know that this is convergent, then it is a linear functional on W. And this is not just an arbitrary linear functional. We can also show that it is a conformal block associated to the Riemann surface after solving. Okay, so this is the one of the main results of our new paper. Okay, so this is the solving part. And in our series of papers, we always talk about the word solving factorization. We always view them as together. So the solving means one direction and factorization means the other direction. I guess I feel that in the literature, different people will, when they talk about solving and when they talk about factorization, I always have the feeling that different people have different understanding of these two words. But in my talk, I kind of view the factorization as the opposite construction of the solving. What solving tells you that, okay, you can construct a higher genus conformal block from a lower genus conformal block in terms of this contraction. And the factorization is the opposite. The factorization, so if the factorization property holds, it means that you could get higher genus conformal block from the lower genus conformal block by taking this contraction. But the problem is that this factorization property does not always hold.
What happened?
Okay.
Okay. Immediate why is this? Let me check the video. Okay. Okay now. Share.
Maybe you just first scan the
version of the if I share it. Actually. Okay. Okay, it's fine.
So unfortunately, the factorization property does not always hold, and this is the really interesting thing that is related to my the main thing I want to show in this talk. About the question of when is this factorization hold, the answer is when your VOA is rational, which means that all the modules are completely reducible. The answer is always yes. This was proved by in order to get this one, you have to combine a very important factorization formulation of Damdolin and Garcia, and one of my solving results. We combine them together, then you can show that okay, this is true when V is rational, but if V is not rational, then this is only true for disjoint solving, but this is in general not true. For. Oops. Oh, okay. So, but before that, I want to give you some examples that show you how this solving factorization stuff is related to something that the first is that okay, because I have a VOA module n, then the vertex operator could be used. So the vertex operator looks like this. It looks like y of v and Z is a complex number, non-zero complex number, you can let this act on a element of my module M, and this is inside the so-called algebraic completion of M, and you can pair it with element inside a gradient to get a number, and this could be viewed as a linear functional on V tensor M prime. So this linear function is a conformal block associated to this genus zero sphere with 3 mark points, where at point 1, if I put Z to be 1, then at point 1, I put this module V, where at 0, I put M, and at infinity, I put M prime. So this is one of the most important examples of conformal blocks in my talk today. And if you do the Sony construction, do this Segal Sony construction, if you solve this the point 0 with the point infinity, you get a torus, right? And algebraically, what you do is that you just take the contraction, or you just take the traces, and you get this the linear function after solving. But you notice that there is a Q here. What is Q? The role played by Q is that because the complex structure of your torus depends on how you choose for the local coordinates. If you scale the local coordinates at one point by some complex variable Q, then the complex structure of the torus will rely on this Q. So you have this Q to the power L0, which accounts for the certain kinds of change of coordinates. Okay, this is not a very important thing for my talk today. And another thing is that you may notice that there is a slight difference between the formula here and the formula that I gave you several pages before. Is that previously when I talk about modern invariance, there is a L to the power Q to the power L0 minus C over 24, but here there's no C over 24, right? There should be some explanations to explain why I do not include this C over 24, but I prefer not to explain it. It could be explained it. Well, the rough reason is that, okay, I have a connections, which is, these conformal blocks, they form the connections over the modular space, and you have this connection is modern invariant, but this construction is not flat. It's only flat up to a projective term, which relies on this central chart. And it's for that reason that this expression is not parallel under that modular invariant connection. But there are some stories, but that story is not quite that closely related to my talk today. So I prefer to not say too much about that. But if you really want to explain all these things rigorously, you have to cover these connections, these kind of things. But for my talk, I prefer to ignore them at this moment. And I just want to point out that the key, a key ingredient, and probably the most important ingredient in Drew's proof of the modern invariance, is to prove the genus 1 factorization, which means to prove that any genus 1 conformal block could be written in this form. Okay, so this is the most important step in Drew's proof of the modern invariance. Okay, and Drew's result, as I said before, Drew's result fails for irrational VLAs, and the failure of Drew's result, it gives a very good example. It shows that it is a typical example showing that if your VLA is not rational, then the factorization might not hold for self-solving, because the first picture is a self-solving, right? You solve these 2 points, you get a torus. This is self-solving, and it suggests that the self-solving does not hold in general. The factorization does not hold in general if your geometric setting is a self-solving. But it turns out that for disjoint solving, the factorization still holds. So one of our preliminary version of the solving factorization theorem is that, okay, if you only consider the disjoint solving, then you can still get this factorization. Your higher density conformal blocks can still be recovered from the lower density one by taking the Segal solving, or just taking the usual contractions. Okay, so it seems that at this point, you still cannot figure out how this solving stuff is related to the pseudo-traces, because pseudo-traces is more complicated than just taking the ordinary contractions. So in the following, what I will do in the following slides is first I will show you what is a pseudo-trace, and I will show you how pseudo-trace could be explained in our framework. Okay. So I will give you a very quick lesson of what is a pseudo-q-trace in the version of Eric and Nakatomo. So our starting point is a V module N, and so M is a V module, and M prime, the graded dual, is also a V module. So you see M tensor M prime is a V tensor V module, right? And we know that this vector space is canonically a non-unital subalgebra of the endomorphism of the algebra of linear operators on M. Okay, the reason that it is non-unital because the identity element is well, as long as your M is infinite dimensional, this elements here is regarded as the endomorphism cannot be the identity map. So it's in general not a non-unital subalgebra. Okay, so I call this subalgebra to be M with superscript 0 of M. Okay, and it has a subalgebra and A0M. It is defined to be all the elements inside N0M, which okay, I forgot to mention what is A. So A is the subalgebra of the opposite of the endomorphism. Sorry, it's the maybe I should use the cursor to show the online audience that yeah. So there's a typo here. It's not the NAM. It is the NVM. It's the endomorphism with respect to the V action. Okay, so there's a typo here. So on the blackboard, it's the NVM op. Okay. So so A is the subalgebra of NVM op, and because NVM is necessarily finite dimensional, so A is also finite dimensional, and so we can consider NA0M to be the elements of all N0M which commute with the action of A. In particular, the vertex operators always belong to this NA0M because the vertex operators commute with the action of A, right? And in order to define the symmetries, I have to assume that N is projected as a right A module, and in that way, there is a canonical way using this kind of projected basis to construct the pseudo-trace, but this pseudo-trace construction will give you a symmetric linear functional on NA0M from any symmetric linear functional of A. So if I call omega to be a symmetric linear function of A, then this new symmetric linear function on NA0M is called a trace with superscript omega. Okay, so this trace superscript omega is called the pseudo-trace with respect to the omega. So there's a canonical way to define this. Okay. In order to define the pseudo-q-trace, we just need to put this vertex operator times q to the power L0. You plug this inside this trace of omega, you will get a genus non-conformal block. Okay, so this is the pseudo-trace construction in the setting of Arito Nakatomo. Okay.
Is the trace positive?
No, what do you
Like if I put trace omega of
no, it's not positive. It's not. It's then I consider all the possible symmetric linear functions. It could be any complex scalars.
Like it depends on omega. Like if I pick the right omega.
I don't expect it to have any positivity. No, I don't. I think that only in a rational and unitary case you'll get some positivity, but in this case you won't get this.
I was asking because I want unitary.
Okay. So this is very different from the unitary case. Okay, so in this class, I will start to explain how to realize the pseudo-q-trace in terms of the previously mentioned Segal sewing. So our sewing factorization theorem tells you that any genus 1 conformal block could be realized by sewing two genus 0 conformal blocks by taking this joint sewing operation. which means that here on the left-hand side, I have a sphere with 3 mark points. On the right-hand side, I have a sphere with 2 mark points, and I glue the 2 points on top together. I glue the 2 points at the bottom, and then I'll get a genus 1, right? So for here, for the sphere on the left-hand side, I need to choose a conformal block, which is a linear functional on V tensor X prime. So V itself is a module of V, and X prime is a contragradient of X. X is a V tensor V module. Okay, so the left-hand side is a conformal block associated with the sphere with 3 mark points. The right-hand side, I choose another conformal block called tau, associated to the sphere with 2 mark points and the module X. And then if you sew these two conformal blocks together by using the contraction, then you will get according to the previous mentioned result, you will get a genus 1 conformal block. And our sewing factorization theorem will tell you that every genus 1 conformal block arrives in that way. So in particular, if you construct a genus 1 conformal block using the previously mentioned pseudo-q-traces, then the pseudo-q-trace can also be realized as the sewing of some psi and some tau, or a linear combination of them. So the natural question is how to give a direct realization of a pseudo-trace construction in terms of these psi and tau. And here's the answer. Recall that in order to define the pseudo-q-trace, I have a associative algebra A, which is a subalgebra of n v0 n, right? And I assume that n is projected as a right A module. And so now I take this x, I want to get a V tensor V module x. I just define x to be the NA0 n, because NA0 n is a V tensor. I mean, at least it's obvious that it is a subspace of M tensor M prime, right? And M tensor M prime is a V module. And using the fact that this NA0n commutes with the action of A, using the fact that it commutes with A, you can either show that it is invariant under the action of V tensor V. So you can show that this is a V tensor V module of M tensor M prime. So you can just say X to be this algebra, but now I view it not as an algebra, but as a V tensor V module. So this tells you what you should put this X as in order to realize this pseudo-q-trace in terms of the pseudo solving. And what about this psi and tau? For the tau, you just take it to be the pseudo-trace of omega. And what about the psi? If you still remember, firstly, we have this, okay, if you remember this, we have a phi here, right? We have a phi here, which is a conformal block. It is a linear functional associated on V tensor M prime, but in our perspective, we can descend it to a linear functional on V tensor X, I should say X prime. X prime is a kind of quotient of this. And then you can descend that linear functional to, this expression, it can descend it to a conformal block associated to V and the contragradient. This NA0n is the contragradient module of NA0n. So this gives you what this psi is, and it's not hard to show that the solving of these two conformal blocks is the same as the pseudo-q-trace. So this explains how to view a pseudo-q-trace in terms of the Segal's solving construction. Okay, so this is one direction. It shows you how to go from the pseudo-q-trace to the Segal solving. Okay, so I think this is one half of my talk, and as you can guess, the second half of my talk is to go the other direction. I have to explain, at least in genus 1, how to realize this Segal solving, this solving factorization theorem, go from that side to the pseudo-q-trace side. Okay. To discuss the other direction, I need to do some more preparations. Okay. We have to give a more precise version of the solving factorization theorem, which also relates the dimensions of spaces of conformal blocks before solving and the dimensions of the spaces of conformal blocks after solving. Okay, and to talk about that more precise version of the solving factorization theorem, I need to introduce the notion of zero fusion product and fusion product. In some way, this is a homogeneous analog of the well-known fusion product. I mean, what people usually talk about fusion product is a kind of genus zero fusion product. But we can also talk about homogeneous fusion product. So the setting is that okay, I have this Riemann surface, compact Riemann surface with some mark points. I separate the mark points into two groups. The blue ones are regarded as the incoming points, and the right hand side are, in some sense, the outcoming points. For the left hand side, I fix a V-tensor n module. Suppose that there are n mark points on the left hand side, and on the right hand side, it is indeterminate. So I just leave this blank. So I just fix the module on the left hand side. So you just think about you putting the input is on W, and there is the output. I mean, you could on the right hand side, you could put some module. There are many possible choices of modules, and whenever you fix a module n, which is a V-tensor n module, you can choose. You have a lot of choices of conformal blocks, and there is a universal way to formulate these things. That is, so there is a universal things. Well, this is really the definition of zero tensor product. It is a V-tensor n module called a box backslash W, and together with this trivial letter gimel, this is a conformal block associated to this data, satisfying a universal property such that any module you put on the right hand side and any conformal block you choose could be factored through this through the canonical conformal block gimel and a homomorphism. So in some sense, it says that you can use the homomorphism to represent any conformal block on the right hand side. So this really looks like, as you recall the definition of, let's say, tensor product of over a field or a ring, and this is very similar to the definition of tensor products of modules over a ring, right? So this is the dual tensor product, and or more precisely, the dual fusion product of W along this geometric Riemann surface, theta the Riemann surface X, and this gimel X is called the canonical conformal block, and the countergradient of this dual fusion product is called the fusion product. So as a typical example is that if you have on the left hand side, you put this is W1, this is W2. Well, each of them is a V module, which means that here you should take W to be a W1 tensor over C, W2, so that this W is a V tensor V module. Then if you take X to be this data, then what you get is what you get for this fusion product is the usual fusion product that we talk about when we talk about the tensor category of VOA modules. Okay, so this is really a higher genus, more general definition or setting for the notion of fusion products, and this is this theorem, the existence of this zero fusion products and fusion products and canonical conformal block is not trivial at all in the non-rational case, and this existence is one of our main results in our first series of papers. So this is the first paper here, which we post on our last year. Okay, and with the help of this zero fusion product, we can. Okay, so before that, we have a example in the rational case. In the rational case, if you I'm sorry that here I kind of switched the orientation. Here I'm going from the right to the left. So the input points are on the right, and here you put W1, W2, and W3. The two mark points on the left are outgoing points, and the dual fusion product could be determined, could be written down explicitly using this formula. Okay. Okay, so with the help of the notion of fusion product and dual fusion products, we can talk about our more precise version of the Thorne factorization theorem. It's a we can describe it in terms of an explicit isomorphism of vector spaces. Roughly speaking, it tells you how the higher genus conformal block could be related to the lower genus conformal block. Look at this picture. Suppose that I have a higher genus combined surface, and I group the mark points into two groups. On the left-hand side, I associate a module W. On the right-hand side, I associate a module N. So what the Thorne factorization theorem tells you is that you can replace the whole green part with this red fusion product. Okay, so this vector space, this space of conformal block could be replaced by that one. So you have a isomorphism from the left-hand side to the right-hand side. This isomorphism is explicitly defined in terms of the solving with the canonical conformal block, because we see that here you put the fusion product of W. So here in order, because I want to solve these red mark points to these red mark points. So if you want to solve these together, you really want these two set of modules to be convergent to each other. So this is the fusion product. This is dual fusion product. And then for the left hand, for the green part, I choose the conformal block to be the canonical conformal block, the gimbal X, and you use this solving construction, you can get a higher genus conformal block. In our theorem, it tells you that this so-called Thorne factorization map is a linear isomorphism for the Thorne factorization isomorphism. Okay, so this is our precise version of the Thorne factorization theorem, which will appear in the third part of our series of paper. Probably will be posted on arXiv next year. Okay. Okay. So after talking about this general genus stuff, I will turn to the special case of genus 1. I will show you how this genus 1 special case of the Thorne factorization theorem will give you all the pseudo-q-traces. So, for example, in the first page, if you take the Riemann surface alpha going to be the genus 1 stuff, then what you get is, well, this picture really specialized to. Okay, I want to turn to the next page.
Okay. Oops.
Okay. So you see that this is the you see this corollary, right? And here this is a special case of the Thorne factorization theorem. Okay. This is the genus 1 torus, and if you replace the Thorne factorization theorem shows you that you can replace this whole green part with the fusion product of V along this Riemann surface with one input point and two outgoing points. Okay. So this is so you see that this dual fusion product is a V tensor V module. Okay, so this is this V tensor V module was first studied by Haijun Li, and Haijun Li called this to be the regular representation of V, because he thinks that this regular representation is similar to the group algebra of a finite group. So he called this regular representation. And so at least our Thorne factorization theorem tells you that we have this isomorphism, which establish an equivalence between the genus 1 conformal block to this genus 0 conformal block. So you see on the right hand side, it is the space of conformal block associated to the sphere with two mark points, and for the the V tensor V module that you should associate to that two mark points is the fusion product of V with respect to the P. Okay, so P is the geometric data on the top right, in the first one on the top right hand side. Okay, so this is the special case of our Thorne factorization theorem. And if you are not familiar with this fusion product V, then I can show you an example. In the rational case, this fusion product V is just the direct sum over M tensor M prime, where M goes through all irreducibles to equivalences. Okay. So, okay, I will show you how to get the pseudo-q-traces. But in order to get the pseudo-q-trace, I not only need this box tensor V to be a V tensor V module. I also need more about that. We can actually show that it has a natural non-unital associative algebra structure, which is compatible with its V tensor V module structure. Okay, so the really good thing about thinking about it as the associative algebra is that we can compare the model category of associative algebras with the model categories of VOAs, and in order to relate these two categories, you cannot just use an arbitrary representation or left module of this associative algebra. I have to consider a special class of associative algebra called what we call quasi-covariant algebra left modules. But the main reason is that because this associative algebra box tensor V is not unital, it follows that not all left modules are quotients of free modules. So in order to get good left modules, we have to look at this quotient of free modules. So we call these modules to be quasi-covariant left modules. And we also want my modules to be not only quasi-covariant, but also finitely generated. So I call these finitely generated quasi-covariant modules to be coherent modules. So for example, this algebra itself is quasi-coherent as a left module of itself, but it is not finitely generated. In general, it's not finitely generated. Okay. If you really want to get a finitely generated quasi-coherent module, you have to, for example, you have to multiply to the right-hand side of this algebra by some endomorphism, by some idempotent to get some finitely generated F modules. Okay. So okay, after I have selected a good class of left modules of my associative algebra, I also want to construct a functor from the category of V modules to the category of the left modules, coherent left modules of my associative algebra. So in order to define this functor, I have to use the universal property to record that if I start from a V module in, then I can use my vertex architecture to define a conformal block associated to the 3-pointed sphere, where at each 3 points I put the V, N, and N prime. Right? This is a linear function, but this is the conformal block that has appeared in my talk several times. And now record that we have the definition of dual fusion product. It tells you that this conformal block phi could be factored through a homomorphism from M prime tensor M to the dual fusion product. Okay, so in other words, I get this. This is a this morphism. This is a V tensor V morphism from M prime tensor M to dual fusion product V. And if you take the transpose, or more precisely the graded transpose, you will get a linear map from the box tensor V to M tensor M prime, which is just the N0 of M. And it turns out that this transpose is also it's clear that it's also a V tensor V module. Okay, so this morphism is the map that I need in order to define the associative algebra module that corresponds to the VOA modules. More precisely, since M is a VOA module, we can also show in a future work we will show that this pi m is not only. We can show that this pi m is not only a V tensor V module homomorphism. It is also an algebra homomorphism. Okay. So therefore, we can use this pi m to define on this vector space M the structure of a left module for that associative algebra. And it turns out that this left module of my associative algebra is coherent. And moreover, we can show that if n is a projective generator in the category of V modules, then this pi n, this representation is faithful. What it tells you is that you can, if you choose your n to be an arbitrary associated projective generator, then you can use this. You can use the algebra structure of the endomorphism algebra of n to describe the algebra structure of the box times V, because this map is faithful. So it faithfully it remembers the associative algebra structure, the endomorphism algebra of n. It remembers the associative algebra structure of the box times V. Okay. So this is my proposition, which tells you how to define the functor. And once I have this functor, we can compare the category. It's a very nice equivalence theorem. It tells you that the previously defined functor is indeed a linear equivalence from the linear category of V modulus to the linear category of the coherent less modulus of this box tensor V. And the right hand side is this coherent category is indeed also a linear category. Okay, and so it means that once we have this equivalence of categories, we can reduce certain parts of the study of the conformal blocks to the study of the associative algebras. For example, you can reduce the study of projective V modules to the study of projective coherent left modules of that associative algebra. So let me call my, okay, so in this theorem, I choose M to be a projective generator of a V module. So according to the previous theorem, I told us that M is also a projective generator inside the category of coherent left modules of the associative algebra box tensor V. And now I take A to be the opposite of the endomorphism algebra of M with respect to V, which is, so you see that these two endomorphisms are the same because of the previous theorem about the equivalence of categories. So I take A to be this finite dimensional unitary algebra, and because N is the projective generator, you can show that N is projective as a right A module, and therefore we can define a pseudo-traces. And we also know that at the beginning, initially, my pi m is a map from box tensor V to n0m, but we can also show that its range is inside the na0m, just by using the fact that A commutes with the vertex properties. We can show that the range of pi m is inside this n0am, and therefore we can use this pseudo-trace map. This pseudo-trace map originally it sends a symmetric linear functional on the endomorphism algebra to a symmetric linear functional on the na0m, and then I can pull back to a symmetric linear functional on the box tensor V, and we can show that this pseudo-trace map is a linear isomorphism by explicitly constructing its inverse. Its inverse is also given by a certain version of the pseudo-trace construction. So these two spaces are really equivalent vector spaces. Okay, so and now we can combine all the previous results to relate the space of torus conformal blocks to the space of symmetric linear functionals on the endomorphism algebra. First of all, recall that the Sony factorization theorem tells us that the space of torus conformal block is equivalent to the space of conformal block associated to the sphere and with two mark points and the module box tensor V. Right? So now we look at the right hand side. Let's look at the conformal block on the right hand side. So this is a conformal block. So in particular, this and a conformal block, an element here is a linear functional on the box tensor V. And it turns out that the linear functional is precisely a symmetric linear functional. So this is the second line, the second equality is easy to see. Okay, so So it tells us that the conformal block, torus conformal block is the same as the space of symmetric linear functionals on the box tensor V, and the previous theorem tells us that the space of SLF on the box tensor V is isomorphic to the SLF of the endomorphism of V, and the orthogonal algebra of M with respect to V. So we combine all of them together, we obtain this isomorphism. So this is an isomorphism from the space of torus conformal blocks to the space of symmetric linear functionals on the NVM. And this isomorphism is implemented by a composition of the Stirling factorization isomorphism and pseudo-q-traces construction. And this isomorphism is previously conjectured by Gainutdinov-Runkel. And it turns out that this isomorphism is a I feel that this is to my knowledge, this is probably the first formula for computing the dimensions of torus conformal blocks that is both general and practical. So first of all, it's clearly a general formula, right? It applies to arbitrary cyclical finite not VOAs, even not necessarily self-field, because there are many important classes of cyclical finite VOAs that are at least conjectured to be not necessarily self-field. For example, the triplet, the W algebra W23, some examples. And this is a general formula, and it is also useful. It could be used to do some calculations to compute the dimensions of conformal blocks. For example, if you take my V to be the triplet algebra WP, it was known before, due to the work of Adamovich and Milas, that the dimension of the torus conformal block is 3p minus 1. The method they use to compute the space of conformal, the dimensions of space of torus conformal block is by combining two results. First of all, they use the modular differential equations to get the lower bounds. They show that the lower bounds is 3p minus 1. And then they study the Drew algebra, and the result on Drew algebra give them a upper bound, which is also 3p minus 1, and then they combine them together. They show that this dimension is precisely 3p minus 1. And now using this formula, using our formula, we can give another proof without using the modular differential equations. Here's the argument. So we know that it suffices to compute the dimension of symmetric linear functionals in the morphism algebra of any projective generator N. But in 2009, Nakatomo and Tsuchiya, they showed that the model category of the triplet algebra is isomorphic to the category of finite dimensional representations of the restricted quantum groups UQXL2, where Q is e to the power I pi minus over p. So according to our formula, it shows us that so this formula, so it shows that there is according to this isomorphism, we know that in the category of mod WP, there is a projective generator whose endomorphism algebra is the UQSL2. It's because for the category on the right hand side, there is a very standard projective generator, which is the algebra itself, right? So this algebra itself is a projective generator. So it also corresponds to a projective generator of WP. So therefore, this projective generator also has the endomorphism algebra to be UQSL2. So therefore, we can take this NVM to be UQSL2, but show that the dimension of conformal block is the dimension of the SLF of UQSL2. And because this UQSL2 has a non-degenerate symmetric linear functional, so therefore, the space of SLF is isomorphic to the center of that quantum group. And it was known before that the center has dimension 3p minus 1, so combine them together, we could show that the dimension of the conformal block is 3p minus 1. So this gives an example of how to use that general formula to explicitly calculate the dimensions of torus conformal blocks. Okay, so I think I'm going to stop here. Thank you very much.
And this first stop recording.